So now we are well into talking about systems of equations, and section 5.2 is going to be all about um, a new way of looking at systems of equations. We're gonna step into kind of a new type of math, a new type of thinking. Um, our whole lives we've been doing math with numbers and arithmetic and powers, and now we're gonna learn that there are in fact whole other sets of um, objects and operations out there. And we'll just start to step into that today with what are called augmented matrices. So we've been concerned with solving systems of linear equations, which look like this. They look like, I guess if you're going to write them in some general way, x11 plus x12 all the way to x1n. This would be the first row. And all the way down x21, x22 to x2n, all the way down to the last row, and so on. And then these, I'm writing my constants. Well, I guess all of these are technically constants. These are supposed to be numbers uh, when you get down to it. This may not have been written the best way. This should be maybe a11 x1. But the idea is because I was thinking of a matrix when I wrote this, but you have a n rows and you have, in this case, n columns. And I say make a note here because this is a square system. And um, I'm noting that because this is just a special case of a system of linear equations. Not every system is square. In a square system, you have exactly the same number of equations as you do unknowns, which means it's possible that you have a unique solution, which is really what students like, because then you're just solving for x and everything feels right. But even with a system of, even with a square system, you could still have um, multiple or infinite solutions. It leaves the possibility that you have a unique solution. But not every system has to be that way. In general, you would write um, m rows and n columns so that they could be different numbers. So you could have a system that's a long, skinny system, or a big, fat system where you have lots of variables and not very many equations. So, right, you could have, x1 plus to xn equals c1, and then x1, xn equals c2, and that's it. So you have this very fat system. Or you could have x1 plus x2 equals c1, all the way down to x1 plus x2 equals cn, and you could have a very skinny system. So there's a very long, skinny system here. Even though it doesn't look visually like that, the dots mean that there's a lot of rows there. So you could have this, or you could have that. So far we've learned two ways of solving these. The first way we've learned is graphically. Right? What would we do? We would literally draw out our lines, x and y, and then we draw our system of equations as lines. So this might be line 1, this would be line 2, and the point at which they intersect is our solution, because that's the point that makes both of the equations true at the same time. The issue is that we're not able to really think beyond 3 dimensions if we do it this way. Even at 3 dimensions, it gets ugly to graph and try to see. Can you imagine graphing in a 3D space? It's not a 3D plane. I think I said 3D plane before. 3D space. Try to graph 3 different planes. I mean, already I'm not very much of an artist, but you see, just it gets cumbersome trying to draw planes on a piece of paper. And so this is nice because, like I said, in fact, it's important. I would say not just nice and cute, but it's important to have a visual idea and an intuition of what it is that's happening, and not just be moving symbols around. So I think it's very important to know that there is some sense of an intersecting of planes when you have a linear system of equations, or we're hoping they intersect, I guess, if there's a solution. So, but that's not the best way to solve it, really. That's a way to learn what the idea is. Um, Another way to solve it is by substitution, right? And so we might have x plus y equals 3, and then negative x plus y equals 7, and we call this equation 1, we call this equation 2, and we might solve equation 2 for y, and we get y is equal to x plus 7. And then we would plug that into equation 1, and then we'd solve for x and so on. And we did it last time, so I won't do it again. And I wouldn't want to throw this away entirely, but I would say that you won't see this as being applicable for maybe a long time. This might be applicable if you were to really do real world problems, and actually write codes and programs. In my project in graduate school, I realized that um, this substitution method can be useful when you're writing a code. But it's kind of in the back of my mind, and it's a little tiny piece of my memory that's not totally clear. But I think computationally it can be what we would say computationally efficient for a computer to be using substitution. Um, though I'm kind of supposing that even so. I don't want to say it's totally useless, but for the near future, maybe even for the next couple years, if you're really going to pursue math and or engineering or something like that, I would say it's pretty useless. It's really not what's going to carry you through the theory of linear systems. The method that will carry you through the theory of linear systems is the method of elimination, which you've probably already run into. So we have example 1 on pages 400 to 401. And they say solve this system by addition. So I'm not sure what they mean by solve it by addition, but okay, yeah. So we want to solve this. We'll call this equation 1, and we'll call this equation 2. So if we multiply um, equation 1 by 5, we get 15x minus 10y equals 8. And then if we multiply 2 by 2, then we get 4x plus 10y equals negative 2. And then if we add these together, we get 19x. These go away, and then this is equal to 6. So we'd say plus 0y equals 6. And now we have an equation just for x. So we would say, and really you might call this equation 3. Actually, well, for now let's call it equation 3. So 19x is equal to 6 means x is equal to 6 over 19. And then you could plug this into either equation 1 or equation 2. So what we'll do is plug it into equation 2. And we get, okay, how about I don't know how to do math. I was supposed to multiply this multiply this by 5. So this is 40. And then if I add this, this is 38. Okay, so x is really equal to 38 divided by 19, which is 2. Sorry about that. So we plug this into 2, and we get 2 times 2 plus 5y equals negative 1. So that means 5y is equal to negative 5. So y is equal to negative 1. So I have my y and I have my x. Okay? So the solution is, and we want to get in the habit of writing it as a point, is equal to 2, negative 1. This is where these two lines are overlapping. Whoops, sorry about that. Oh, man. Well, there it is. You could fill it in, maybe pause the video. Sorry if I did all that without you seeing it. But what I did was I just multiplied one of the equations by a number, added them together, and that got rid of y. And then I was able to solve for x. And then I made a mistake. This should have been 19x equals 38, and then I got x equals 2. And I plugged that into the second equation, and I got 2 times 2 is 4 plus 5y, so y ended up being negative 1. And the solution is a point, xy, to negative 1, where these two lines are overlapping. So it's right here. So I have two lines. I'm not exactly sure what they look like, but let's suppose they're like that, and they overlap right there at that point. I don't need to draw it in order to do it. Now, this leads us into a very, very important concept that I was able to multiply the equations by a number and add them together and find the solution. So this process of multiplying equations and adding them didn't change what my solution was. I could have just as well done this by substitution, like up here, or I could have graphed it and I would have gotten the same answer. So a question is, how can we change our system without changing the solution to the system? How can we change our system without changing the solution of the system? Well, what if we switch the two equations? Right? So we had 3x minus 2y equals 8, and then 2x plus 5y equals negative 1. Well, this is my 1 and this is my 2. What if I switch the order? If I did this, 2x plus 5y equals negative 1, 3x minus 2y equals 8. So now this is my 1 and this is my 2. Well, the obvious answer should be that it makes absolutely no difference. I switch the order and I still have the same two equations. They still both have to be true, and my x and y solution will be the same. So no change. Same solution. Okay. What if we multiplied one of the equations by a constant? By some alpha not equal to 0. Alpha is it has to be a non-zero number. So let's say I did 1 is 3x minus 2y equals 8. 2 is 2x plus 5y equals negative 1. And then let's say that I multiplied 2 by, I don't know, 4. Well, what did we do? We actually multiplied 2 by 2. So we get 3x minus 2y equals 8, and then 4x plus 10y equals negative 2. Surprisingly, though, and this is not as clear in my mind as this, but this doesn't change the solution either. So no change. All right. What if we added a multiple of one equation to the other? So, which is really what we did. I can take equation 1 and equation 2. Again, 3x minus 2y equals 8. 2x plus 5y equals negative 1. And I did it to both. I multiplied 1 by 5 and 2 by 2. And I got 15x minus 10y equals 40. And 4x plus 10y equals negative 2. And then I added them together. So you could say that I added a multiple of this equation to a multiple of the second equation, which really, remember, since multiplying an equation by some constant doesn't change anything, I kind of used this step in this step. I don't know what else to call it. But so I was able to multiply the equation 2 by something, and it didn't change it, according to this rule that we have here. Then I added a multiple of equation 1, and that doesn't change it. So no change yet again. So we have 3 rules. And that's what theorem 1 is on page 400. And this is equation operations producing equivalent systems. Okay. So 1. 2 equations can be interchanged. Two, sorry, 2, an equation can be multiplied by a non-zero constant. Right? And we usually call that some alpha not equal to 0. At least that's what my book called it, so that's what I'm calling it here. But alpha, it's just a number. Don't be intimidated by the notation. It just means it's a constant. So alpha could be 5, like here, or 2, whatever. And it doesn't change the system. 3, and this is the most important one. Really, this is number 3 is basically the process of elimination. You can add a constant of a constant multiple, sorry. One equation can be added to another. All right. So this this along with the next point that I'm going to make is really the beginning foundation of the idea of matrices and linear system and linear equations, or I should say linear algebra. It's really starting to build that foundation where I'm able to interchange things, and so I can define. Um, we may not say it in this lecture, but I think in the next lecture we'll say, certainly in chapter 6, we'll begin to define something called matrix multiplication, which is um, especially elementary matrix multiplication, which is really just doing this. It's interchanging rows and columns and multiplying things by constants, but it becomes its own operation, and matrices become their own objects, and we can think kind of in a bigger picture, so we don't have to think about the details, these little kind of annoying details, so much. And it even becomes a little bit more interesting, and you can solve more general, more powerful, I think, and come to more powerful conclusions. So what is the essential information we need to solve our system? Do we need to keep writing x and y over and over again? Here, you see how we have 3x minus 2y equals 8, and then 2x plus 5y equals negative 1. Do we need that? Well, the answer is no. We could just as well write 3x minus 2y equals 8 and 2x plus 5y equals negative 1 as 3, negative 2, 2, 5. And then we write a dotted line here, 8, negative 1. And then we write a bracket. Excuse me. And this is what's called an augmented matrix, which really is just another way of obviously writing a system of equations, but really writing what's called a what's the name for that? I guess a matrix equation, ax equals b, where x is the unknown vector x and y. So once we define matrix multiplication, this will make more sense. B is this thing right here. So we would say b is equal to, and we write it as 8, negative 1. This is a point. This is my x value. This is my y value. Instead of writing it sideways, I'm writing it vertically. And then a is this whole thing here. So this is really all we need. We don't need to keep writing x and y. We just need the coefficients and the constants. And then we need these equation operations, which really become row operations for matrices. And we can solve this system. So the constant coefficients, and I forgot what I was calling this. I wrote parentheses here for some reason. The I guess I would call this the matrix elements can be written as a matrix. Well, that's kind of redundant. Forget that. Okay, so the constant coefficients can be written as a matrix. That's the point. And then we want to remember those three row operations. Okay, that we use when we're solving a system by elimination. Okay. So matrices. This is what we're building up to here, is matrices. A matrix is really nothing like what the movies might make you think it is. When the movies, a lot of that stuff in science fiction really, a lot of times is very disconnected with what is really happening in the field. So a matrix is really just a set of rows and columns of numbers. So it's a set of numbers written in rows and columns contained in brackets. So given a system of linear functions, 3x1 plus 4x2, x1 minus 2x2, we would write 3, 4, 1, negative 2. This is a matrix right here. See, what we had before was an augmented matrix, which really isn't what you think of when you think of a matrix as you grow in linear algebra thinking. You think of just the row and column without the equal sign. We see we don't have the equal sign here. We're just worried about these coefficients. And then see, this is why I'm saying a set of linear functions. Once I set them equal to something like here, then I would call it a system of linear equations. And I would write it as 3, 4, 1, negative 2. And it's nicer, instead of writing an augmented matrix, I'll do this once here and probably won't do it again until chapter 6. But you might write xy equals 1, 7, right? This is really ax equals b. But for now, we're writing it as, and I'm out of room here, we're writing it as 3, 4, 1, negative 2, dot, 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 1, 7. And then we'll define our row and column operations. So how would we solve this when it's written as a augmented matrix rather than a system of linear equations? So remember theorem 1. We have a set of rules that is almost exactly the same for matrices, and that's page 405. Really, eventually it should seem redundant, almost, that you would call theorem 1 its own thing, and then you have this new theorem, theorem 2. They should seem redundant. They're saying exactly the same thing. We call it a row equivalent matrix. So row operations producing row equivalent matrices. Okay, so here's row operation 1. 2 rows are interchanged. Okay, 2 rows are interchanged. Well, that's just like where I said over here that we're allowed to interchange 2 equations. Okay, so I could take, of this augmented matrix here, I could take this row and switch it with this row, and it's a row equivalent matrix. It's not the same matrix, but it's a row equivalent matrix. All right. Number 2, a row is multiplied by a non-zero constant. And they call it k, so I'm not going to call it alpha, I should call it k. K not equal to 0. So, again, I go back to here, and I remember I can take an equation and I can multiply it by a non-zero constant. I call it alpha, so I should call it k. So taking an equation, multiplying it by a non-zero constant, doesn't change the solution to my system of equations. And taking a matrix and multiplying it by a non-zero constant produces a row equivalent matrix. Right? Great. Now, here's the big one. A constant multiple of any row can be added to any other row. Okay, and again, this is like the third one. This is the process of solving a system by elimination. This is the one that we'll be using the most. So It kind of got cut off here. I said let's solve our system using an augmented matrix. Okay? So we want to solve 3x1 plus 4x2 equals 1, x1 minus x2 equals 7. And this is example 3. Or I should say let's solve a system, but whatever. So first thing we do, we write this as a matrix. So we write it as 3, 4, 1, negative 2. Write a little dotted line, or they just write a vertical bar. 1, 7. We have our bracket. So start getting used to calling them these row operations. Start getting used to calling them like R1, R2, R3. Oh, I'm sorry. Disregard that. We want to call the rows, call this R1 and call this R2, or R1 and R2, and then we'll add them and multiply them and all that stuff. So our objective is to use row operations to try to transform the matrix into this form. So yeah, you wanna get it looking like this. I'll write it out on the side. 1 0 0 1 vertical bar M and N. Okay. So what that produces is that tells you what your solution is. Your solution would be whatever M and N are. Okay, so first thing we'll do is we'll switch row 1 and row 2. Okay, so switch row 1 and row 2. And they write it like this. Row 1 switches with row 2. So now we have 1, negative 2, 3, 4, vertical bar 1, 7. Okay. Second step. We'll add a multiple of a row to another row. So we're going to add negative 3 row 1 plus row 2. And this is whoops. You want to get used to, this can get a little confusing. It says I multiplied row 1 by negative 3. So should this not be a negative 3? And the answer is no. The affected row is the second one. And I'm glad that this book does it like this. The affected row is the second row that you write. So what I end up with is negative 3 times this number plus this number gives me what? It gives me 0. And then negative 3 times this number, which is positive 6, plus this number gives me 10. And then I have to do it to the whole row. So negative 3 times also this number plus this number gives me 1. Okay? And then I just copy down the first row. So you have to be very careful there. Because this doesn't actually change row 1 doesn't actually get changed. The only row that gets changed is the second one that you write when you're doing this row operation, when you're adding a multiple of one row to another row. Get that as a habit, because if you change it, it's gonna mess up your work. So I only change the second row. Now what? Well, now okay, first of all, I'm an idiot. All right, 7 and 1. So negative 3 times 7 is negative 21. Plus 1 is negative 20. So this should have been a negative 20. Okay, I made a mistake there. See, nobody's perfect. Okay, now, um, see, this is almost solved because remember, this is a system of equations. So I should imagine that there's an x here and that this is a number. So I have 10x equals negative 20. So what would I want to do to solve for x? I would divide both sides by 10. So I can multiply the second row by 1 over 10. That gives me 1, negative 2, vertical bar 1, and now I have 1 here equals negative 2. It's not 1 equals negative 2. Really what this is saying is x equals negative 2, right? But we're not quite done because we want to get rid of something else here. And then what we would do is we would multiply the second row by 2 and add it to the first row. And again, we're doing the third row operation here. And we want to remember that when we do the third row operation, only the second thing that we write, the second row, is the one that gets changed. In this case, it's row 1. So I multiply 2 times 0 and I get 0, and I add that to 1 and I get 1. So that doesn't change, which is why you want to focus on getting zeros, by the way. Then 2 times this number, because it's 2 times everything in row 2, 2 times this number plus this number gives me a 0 there. And then I rewrite the 1. Remember, I don't change the second row. So let me just rewrite the whole second row. Be done with it. 2 times this number plus this number gives me negative 3. Now I can see exactly what my solution is, because I think of this as being my column for, oh, this is actually y, you see? See, look at me. This is a y here, not an x. So this is y equals negative 2. So this is my x column, this is my y column. And so my solution is xy equals negative 3, negative 2. And I solve that using row operations and augmented matrices. I would have gotten the same answer if I would have graphed it. I would have gotten the same answer if I would have done it by substitution. But this is really the way to the pattern you want to start building. That really is how you'll solve linear systems, bigger linear systems. Eventually, what it looks like is finding a way to get what's called an inverse matrix. And so you multiply both sides of this, ax equals b, you would multiply both sides by something called an inverse matrix. If I were to take each of these row operations, each one of those row operations could be represented by what's called an elementary matrix, or some matrix, maybe not necessarily an elementary one. And if I were to multiply all those matrices together, I would get the inverse matrix, which I would just call a negative 1. And then if I multiply both sides of this by a negative 1, all of this work would be done, and I would get my solution. And then there's very efficient ways of finding an inverse matrix. So this is all build up to eventually doing that. Okay. So here, what type of solution do we have? We have a unique solution. Right? Remember how we talked about the different ways that linear systems can relate to each other? This is a system of 2 equations and 2 unknowns. So we're in our happy place of R2 of x and y plane, and we have 2 lines that are intersecting somewhere down here, and they overlap there. So this is what we're used to. But we have one solution there. Now we want to solve this system. 2x1 minus x2 equals 4, and negative 6x1 plus 3x2 equals negative 12. So again, we write it as a matrix. So we have 2, negative 1, vertical bar 4, negative 6, 3, negative 12. Okay, great. the goal is, I kind of hinted or said it in passing up that you want to get zeros somewhere. That's kind of a goal, and then you'll find your system gets solved. So if I multiply the first column by a half, and let me also multiply the second column by a third. Let me just do that in one step. Then I'll get 1, negative a half, and a 2. And I'll get negative 2, a 1, and a negative 4. Okay? Then let me multiply the first row by 1 and add it to the second row. Right off the bat, so I don't make a mistake, let me copy down the first row, because that is not changing. Even though I said I'm multiplying it by 2, really in this whole step, I'm adding the step is adding a multiple of one row to another row. So the only thing that gets changed is this. So 1, negative 1 half, 2. So now this is what's changing. So 2 times row 1 plus row 2. 2 times this number plus this number gives me a 0. That's a good thing. 2 times this number plus this number gives me another 0. 2 times this number plus this number gives me yet another 0. What do I do when I get all zeros? That's weird. Well, let's simplify this first row a little bit. Or let's not. Let's maybe think of this as an equation now, as a system of equations yet again. This is saying that, and we got to get used to, instead of calling it x and y, we'll call it x1 and x2. This is the column that would correspond to x, which is now x1, and this is the column that would correspond to y, which we'll now call x2. Let's write this as a system. x1 minus 1 half x2 is equal to 2. So what does this mean? I've reduced this using row operations, which again, they do not change my solution. That's the important thing to remember, is we're preserving the solution. Let me go ahead and solve this for x1. I would get x1 is equal to 2 plus 1 half 2 plus 1 half x2. Well, that's nothing profound. I mean, I'm solving for x, right? The meaning of it is what's important here. x2 now becomes what you'd call a free variable. So I would really, just to write it as something different, because it's a different concept, I would write it as 2 plus 1 half t. So this is a free variable, meaning it can be anything I want. Meaning that my solution, I have an infinite number of solutions now. This is the case where I have both lines on top of each other that I talked about last lecture. So what I have here is I have y equals mx plus b, right? Where my m is 1 half, so I have a slope of 1 half and a y-intercept of 2 for one of my equations. And guess what? The other equation turned out to be exactly the same thing. So I have an infinite number of solutions for this system. So if I were to write it as as a vector, I would write x is equal to 2. I'm sorry, 2 plus 1 half t and then t. I guess maybe it's not time to be writing stuff like that yet, but that's the idea, is that you have you don't just have one point as a solution like we do up here. We have now a whole line of solutions because they're overlapping. They're the same line. Okay, last one, or last example from the book. Let's solve this one. 2x1 plus 6x2 equals negative 3. So I write it as a matrix. 2, 6, vertical bar, negative 3, 1, 3, 2. Right. How do we eliminate stuff? Let's go ahead and switch the two rows. So I'm going to switch row 1 and row 2. And then I have 1, 3, vertical bar, -3. Uh, did See, I did it again. 1, 3, and that should be a 2 now. And then this is 2, 6, -3. All right. Now I'm going to multiply the second row, -2r1 plus r2. Sorry, the first row by -2. So what's not changing? The first row. 1, 3, 2. Copy it down right away so you don't make a mistake of accidentally changing the first row. The only thing that changes is the second thing that's written here. So -2 times row 1 plus this gives me a 0. -2 times 3 is -6 plus 6 gives me 0. Oh, looks like we might get infinite solutions again. Well, let's see. -2 times 2 plus -3 gives me -7. So it's good to remember that this is all having to do with a linear system of equations. So what am I saying here? What I'm saying is that 0x1 plus x2 plus 0x2 is equal to -7. So really, 0 times anything is 0, so 0 is equal to -7 is what I'm saying, which makes no sense. This is a contradiction. Not possible, right? So whenever you get something like that, that means these two lines, there is no solution. These two lines are parallel. That's the other case that we talked about. So I would say no solution, or you would call this an inconsistent system. All right. Okay. So that's the idea behind this matrices and using matrices to solve linear systems. That's the building blocks of it. It gets much cleaner. I mean, this can get annoying, and we're going to use the calculators. I hope to be using the calculators quite a bit to do this because this can get very tedious, and you can kind of get lost in the arithmetic of it when really I want to focus more on the theory and the thinking of it, not the little, multiplying by a half and adding, and that just gets really tedious, and it kind of gets in the way of the enjoyment of the theory because it's pretty elegant stuff. So let me do a few problems from the section. Let's do number 1. It says solve by addition. This is 2x plus 3y equals 1, and 3x minus y equals 7. So if I multiply, see, even now I'm so much in the habit of thinking of rows and columns of matrices. I'm going to multiply this by 3, the second one by 3. So I'll get 2x plus 3y equals 1, and 9x minus 3y equals 21. So 2x plus 9x equals 11x. These go away, and I'm left with 22. So x is equal to 2. And then I could plug this back into the original, either of the originals. So I'll say plug into 2. All right, this is 1 and 2. So that gives me 3 times 2 minus y equals 7. So I'll get y is equal to I'm sorry, that's 6. So it's 6. So y is equal to 1. Y is equal to -1. Jeez, I don't know why that was so difficult. All right, so xy is equal to 2 -1. That's my answer right there. And this is just a point. I mean, xy equals 2 -1. I mean, I could write it this way or I could write it this way. I shouldn't say it's just a point, but it's basically like a point. It's a vector now, and we want to start writing it like this because we want to start thinking of things as column vectors. We want to write our points as column vectors now, because that's how we that's what we mean when we say ax equals b. This x is a, a one column matrix, and just get in the habit of writing things like that. Okay, so that's old stuff, right? Um, Problems 5 through 14 just want you to get used to matrices and how we label them and talk about rows and columns. So 5 through 14, we have these four matrices. A is 3, -2, 0, 4, 1, -6. B is -2, 8, 0, -3, 6, 9, 4, 2, and 0. C is 3, -2, 0. And then D is -4 and 7. So what is the size of A? Well, I don't know what they mean by size, actually. They never define that. I would assume they mean the number of rows and columns, but... Oh, okay. Yeah, they mean n by n. So the size of A, number 5. Well, the size of A is just the number of rows, which is called m. So you would say it's 2 by, and then the number of columns, which is n, 3. So 2 by 3 matrix. So this matrix um, cannot have a unique solution. Well, maybe it can, but a lot of times I've experienced that these matrices tend to have um, either infinite solutions or something like that. So size of C. Well, how many rows do we see? We see one row and we see 3 columns. So you always write the row first. This is the row and this is the columns. Okay? Number 10 is an interesting question. Not really, but I guess a helpful question to teach you the concept. How many additional rows would matrix A need to be a square matrix? So I want to make this a square matrix, and we like square matrices because those are the invertible ones if they are if they don't end up having zeros for their entire rows, but those are the only ones that are potentially invertible. So I would need one more row. Excuse me. Okay. 15 through 26 is getting us used to doing row operations. So let's try number 15. We're given the matrix 1, 4, -3, -6, 2, -8. 15 says interchange row 1 and row 2. Excuse me. So then I just write 4, -6, -8 up here, 1, -3, and 2 down there. Okay. All right, let's try number 21. So again, our matrix that we started with was 1, -3, vertical bar, 2, 4, -6, and then -8. And they want us to write -4 row 1 plus row 2 and then change that into row 2. So again, the only thing that gets affected is the second thing. So we just copy down the first row to get it out of the way and not make a mistake. And then change the second row according to this little formula here. So -4 times 1 is 4. I'm sorry, -4 times 1 is -4, plus 4 is 0. -4 times -3 is 12, plus -6 is 6. Negative 4 times 2 is negative 8, plus negative 8 is negative 16. Okay, and that's it. We're not solving it, we're just doing the raw operations. They're just really giving us baby steps here to get used to it. Number 27. They give us the augmented matrix A, negative 1, 2, 6, negative 3, negative 3, and 12. And they want you to identify the row operations. So what's happened here with number 27 is they've changed it to look like this: negative 1, 2, negative 3, and now this becomes 2, negative 1, 4. So which row operation did we do? Well, we did row operation number, I think it's 2. Yeah, we did um, row operation 2 because we multiplied row 2 by 1/3. I'm sorry, I'm a little bit sick. So, yeah, that's what we did for that. And then number 33 through 50 is really the important stuff. So, and that's the examples I did. So I'm not gonna. I'll do number 33, I guess. I'll do one more. So I'll do. We have x1 plus x2 equals 7 equals 1, and then it says solve graphically. You can use your graphing calculator on that because again, I'm not gonna be emphatic about graphs. They're to give us intuition. They're not to be what we depend on entirely. So we make this into an augmented matrix 1, 1, vertical bar 7, 1, negative 1, 1. And then the goal is to get a 0 somewhere. So I can get a 0 if I say, let's do, let me switch row 1 and row 2. Okay, and then if I add row 1, if I add row 2 to row 1, which one am I changing? The second one. So I just copy down row 2, and then I say, okay, 1 plus 1 is 2, 1 plus negative 1 is 0. I have my 0, and I get excited. And I say, okay, how do I get another 0? Well, first, let's make this into a 1. So you want to focus on getting 1s and 0s. So if you see a constant, if you see like you only have one non-zero thing left in your row, try to get that to become a 1. So I multiply the whole row 1 by a half, and I get 1, 0, vertical bar 4, 1, 1, 7. All right, and then the only thing left to do to solve it is to multiply the first row by negative 1, and then add it to the second row. And so I have 1, 0, vertical bar 4, and then negative 1 is going to be what this is. Added to 1 is 0. And then this doesn't change because it's just 0 plus that. Negative 4 plus 7 gives me 3. So my solution is x, really we want to call it x1 from now on, and x2 for 3. Or as we used to write it, xy, so 4 comma 3. All right. If you really need to start out, you can write this as a linear system. Go back to a linear system. Say this is what was in front of x, and then this was in front of x, yeah, and 1y equals 3, right? So 1x plus, so literally you're saying x must equal 4, and then y must equal 3. All right, I'll post the homework. I haven't decided exactly what it is yet, so have fun with all that.